Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hi, and welcome to today's Australian Water School webinar focused on flooded roadways and vehicle crossings of flooded roadways. It is a topic that we're going to talk about some pretty serious consequences today. And before we get into that, though, let's first of all welcome all of you from around the world. This is a topic not just here in Australia. I see a lot of attendees from the United States, from Europe, from around the world, really. Welcome to all of you today. I hope you are able to get some good design skills out of this, and perhaps some warnings that will allow you to pass along the public service messages that we'll hear from today and hear more about today. So let's introduce our speakers, presenters, panelists for the day. We've got Ben and Carlos. Ben, Carlos, if you can turn on your cameras and just say good day to us. What we'd like to know from you is, first of all, what's your background? What do you do? How'd you get into this business, this field of, providing some advice around flooded roadways? And let us know where you are coming to us from today. First, over to you, Ben.
Hi everyone, thanks for joining us all. I'm from the Water Research Laboratory at UNSW Sydney, and I'm fascinated by anything to do with water, coastal hydraulics. I do a lot of work in those areas, and we have a team of flood specialists here, and it was a really important part of our work to contribute to, what happens to vehicles in flood and helping ensure the safety of people as they are around floodwaters.
Excellent. Thanks for that. Over to you, Carlos. Let us know a little bit about yourself.
Hi, how are you, everyone? Thank you for the invitation to Australian Water School. Well, I'm a hydraulic engineer working at the Queensland Department of Transport and Main Roads, and obviously floodways and low-lying crossings are part of the scope and work here. I've been around for a while, originally from Mexico, but I've been here for 20 years working in all sorts of hydraulics, bridges, floodways, dams, etc. So yeah, happy to share with everyone a little bit of what we do here in Queensland.
Yeah, thanks. If we can have a look at the poll results, let's pop those up for a minute. And I'd like to just know from our presenters here, do any of these answers surprise you? If you go down to the questions about what depth of water it takes to float a small car versus a mid-sized car versus an SUV or a ute, we've got a few different answers there. And I guess the question to you, let's start first with Ben and then to Carlos. Would you have expected these answers? Did people underestimate, overestimate? What are your thoughts?
Well, there's a very big spread there. I noticed that you've got everything from 5 centimeters to 1 meter. But probably those ones where you've got the peak of the bar graph is probably pretty close.
Yeah. Excellent. Carlos, any thoughts on that?
Yeah. In fact, the policies over here, no depth is safe. So if it's flooded, forget it. So don't try to definitely don't try to measure what is the acceptable depth, I will say.
Exactly. And I guess our challenge to you today is to maybe retake that poll at the end, or think about what you would have answered after seeing some of the video clips and some of the research that you can see here. So yeah, have a look at that and give that some thought. We'll bring Ben and Carlos back on with us momentarily. What I'm going to do first of all, though, is make sure we get some definitions squared away. So what I wanted to talk about here initially is just the terminology on what we're calling these crossings. So we've got in Australia, we talk about floodways quite frequently, but if you looked at that spread on the map, we've got a lot of attendees from the United States, and in the US, floodway means something entirely different. So we are not talking about the FEMA floodway, this arbitrary 1 foot rise from encroachments in a 1D model that keeps some of the modeling constrained a bit in the US. That's not what we're talking about. We are talking about low level crossings, floodways. These are roadways that are designed to be overtopped by water at a certain recurrence interval. Now, what I'd challenge you to do in the background, you're coming to us from all around the world. I've listed 1, 2, 3, 4, 5, 6, 7 different different terms that I've run across. You may have more. So in the chat line, this is not a technical Q&A question, but in the chat line, if you can just let us know if there are terms we've missed. If you call these something different in your neck of the globe, do let us know, because I want to make sure that when people Google search for this, for this presentation or for this topic, that we've got some of the terms included here that we'll be addressing today by perhaps a different name. So this is what we're talking about today, floodway crossings. And to put an Australian context onto it, let me just start with this video here and be thinking about this one in the background as you see Ben's research and Carlos's thoughts as well on what it takes to move a vehicle. And here in Australia, this is a uniquely Australian example because you do not want to get stranded here. If you look at this person who got stranded in their pickup truck here, guess who's coming to pick him up? This is a sightseeing tour for crocs. So they are in the Alligator River here looking for crocs, and they have probably found some crocs out there. This is not where you want to get stranded. So that's just a Australian focus on this one. We've got a few messages that we'll be hearing about on, the dangers of crossing flooded roadways, even when they stay intact. This is one from a police photo here in Australia. But when they don't stay intact, again, the problem is that looks can be very deceiving. And so you might think you can walk around in some flood water, and boom, he went completely submerged. You don't know what's under the water, especially in flood. You're not going to be able to see underwater. Would you cross this, would you go across this one here? What's missing here out of this hole? Just remember that looks can be entirely deceiving because all that is just a reflection of water. But again, keep that in mind. You cannot always see below the surface, and you won't know what's going on. And after the flood recedes, there may be something like this to observe. But this might be happening as you under the surface as you observe it and make the decision whether or not to drive through it. So first of all, Ben's going to be talking to us about some examples of what it takes to float a vehicle. And then Carlos is going to be talking about what it takes to design these crossings so that once the floodwaters recede, they're still intact afterwards. So let's start with Ben. If you want to share your screen, over the top of my examples here from Western Australia. We've got some from all around the world as well, some YouTube clips as well that might scare you a little bit, and that's fully by intention. So I can see your screen there, Ben. Over to you, Carlos, and I will turn our videos off until till we come back on after your presentation.
Great. Thanks, Cray, and thanks everybody for joining us today. I'm going to share with you a study that was done here at the Water Research Laboratory a few years ago, largely in the physical modelling space, looking at both full-size prototype vehicles and some scale model vehicles, really focused around what it takes to destabilise a vehicle within floodplains. I've got heaps of content here, so I'm going to have to skip over a little bit and run through it really quite quickly, unfortunately, but we'll do that. Firstly, I'd like to say thanks to New South Wales State Government for their financial support for this project, the IAG, who provided vehicles for the study, UNSW School of Civil and Environmental Engineering, who provided in-kind support, and in particular, my colleagues Grantley Smith and Stefan Felder and the rest of the team here at WRL who were involved in this. Present you some of the background, what causes the instability, how we formulated the problem of stability, the research and the tests that we did on buoyancy and its effect on traction, hydrodynamic forces, and the outcomes of the study. I'm going to start with a little bit of a video reel here to show you some of the sort of get ahead in the right kind of space. So what happens to a car when it goes into floodwaters? Well, we think of cars as these, big, heavy, safe things that drive us around. In floodwaters, they float really easily. You've got this big cabin full of air, cabin and boot, which just basically is very buoyant. The engine, of course, is the heavy part of the vehicle, so the front of the vehicle tends to, sit quite low in the water, and the rear wheels lift. Now you can see the float gauge there on the left. That was only 0.6 of a metre. If we had flows in the water, that flow impacts the vehicle very quickly. And of course, you know, the back of the vehicle being light, we had this tendency for the back of the vehicle to just spin out and be lost. Here's that same clip that we saw from the Alligator River. And there's a few I really like this clip actually because it highlights a few things. One is that key mode of instability where the back of the vehicle begins to slide out. Second is just how little room there is for error. You know, he's on this causeway. As soon as the vehicle starts moving, he's in trouble. Other thing is the size of the vehicles. You saw that truck go through very, very easily. So the mass and the height of the vehicle is really key to the stability of the vehicle, and also take note of this very complex flow conditions that you have here. I've got quite a few videos in this presentation. I particularly picked ones where I knew that people were rescued and saved from their vehicle. Nobody was injured. So you know, don't be troubled by that. There's certainly many people that don't have that. You know, flood waters are dangerous, and worldwide, lots of people continue to die by making these poor choices of driving through flood water. What you see here, this vehicle has lost and has been dragged quite a long way downstream. To rescue the people from the vehicle, some other people have really just waded out across the river and helped them and just helped them walk back. Which shows us another real key thing, which is quite surprising, or not surprising, but not intuitive, is that vehicles are much less stable in floodwaters than vehicles. So the key mechanisms for instability of a vehicle is obviously buoyancy of the vehicle, means it can float. If you've got flows coming from the side, there's this hydrodynamic loading on the side of the vehicle, which means the vehicle will slide. So the hydrodynamic forces overcome the traction forces of the tyres and it slides forward. And if the road is at all uneven, or if there's potholes or there's been damage to the road, you can have toppling to the vehicle. There's a number of other hazards to a vehicle rather than just, you know, being washed downstream. You have a stalled engine, you might have an electrical or a mechanical failure, which means that the vehicle stalls and you actually have to, you know, get out and traverse the floodwaters on foot, which is a hazard in itself. There's a visibility of the hazards, which is a real issue. You don't know where the edge of the road is, you don't know if there's debris on the road, or even if the road may have been completely washed away. You don't know any of those, so that is a real hazard as well. Any debris, you can imagine a tree trunk floating downstream, impact the side of the vehicle, you know, is going to contribute to destabilizing that vehicle and having the potential for it to wash downstream. There's been a number of previous studies. You know, here at WRL, we've got studies right back to the 60s. This was quite a seminal paper that was done and, you know, led to the really early design guidelines for causeways. But we wanted to approach the study in quite a different way. So this actually resulted in a journal paper, and which of course you can access. And a real approach that we wanted to do for this one was to break the problem down into its component forces. What's the traction? You know, how does buoyancy affect traction? What's the coefficient of friction? You know, what's the hydrodynamic, you know, the coefficient of drag on the vehicle? So we really wanted to look at all the different component forces that impact a vehicle. And it's very, you know, at a very high level, it's a simple problem. When the floodwaters, the force of the floodwaters on the side of the vehicle overcome the traction between the tyres and the road surface, the vehicle will shift sideways. So that left side, the hydrodynamic forcing, that's a very standard equation. Anyone in hydraulics or aerodynamics will know that. Key thing for us is knowing that the area, the cross-sectional area of the vehicle is dependent on the flood depth, as is the coefficient of drag. So those things are both impacted by the depth of the water flow. On the right-hand side, the traction force is simply the coefficient of friction multiplied by the weight of the vehicle. So, but of course we have, as we've seen, vehicles are buoyant, so they tend to float. So we've got to take away that buoyancy from the vehicle. There's also, we need to consider the hydrodynamic uplift force. Unfortunately for our study, we weren't able to get a really good measure on that. And so we had to assume it was zero for the rest of the remainder of the study. That's another area of future research. So there's a couple key points that, assumptions that we made at the start of the project. Firstly, is that at that first breaking, that point of losing traction, we said that the car had failed, has potential to be washed downstream. That doesn't always happen. Sometimes a car can shift slightly, regain traction, and then drive off and survive. That does happen. For the sake of this, and we're thinking, broadly about stability of vehicles, as soon as that vehicle loses traction, we consider that to be a failure. Because the rear wheels have so much less traction due to the buoyancy of the vehicle in water, so we're really focused on what happened at the rear axle. We also considered, if you cast your mind back to those videos, all of those videos showed the cars trying to traverse directly across the channel. Our causeways and our bridges are constructed to be perpendicular to the river. You're really trying to get across to the other side as fast as possible. Anybody driving in floodwaters doesn't want to drive in floodwaters. They're really just trying to get to the other side as fast as possible. So we only considered perpendicular flows to the vehicle. There's other studies out there which look at different things. So this is basically what our study looked like. We have a vehicle in a tank. As you fill the tank with water, the vehicle begins to unload off the springs, and if you get deep enough, someone can just get in there and push the vehicle around really easily. If you go a bit further, a bit deeper, well, this is a smaller vehicle, so the water depth isn't as deep as it was for the four-wheel drive, but you can also get the front of the vehicle to move around really easily as well. So our experiment, the first part of our experiment, looking at buoyancy and traction, really started with this setup. We have a winch at the top here, a dynamometer, which is hooked up to a logger. So we're measuring the loading over time, which is hooked up through a pulley to the rear axle of the vehicle. And we're basically pulling the vehicle to the side and seeing what force is there over a range of depths. Oops. This one. So this is just a quick shot of that experiment. It's really quick. It's only happening over a few seconds. We're just looking at that tugging of the vehicle sideways. So what does those force plots look like? Well, we have this, when we start our winch, we're loading up our tires. So the tire is deforming, it's pulling across, it's holding its traction to a point where that traction breaks. And then the vehicle through here is being dragged, and then we stop the test. So we do that across a range of tests, across a range of depth levels. And so we're comparing we're looking at the loading over a number of different depths. We did that across 3 different vehicles, the Yaris, pretty standard kind of sedan, 4-door sedan, very large full drive, obviously is very heavy. It's got a very high pan level. So the pan, I'm going to talk about this quite a lot. The pan is the bottom of the cabin of the vehicle. So when you're sitting in your car, it's what your feet sit on. And Ford Festiva, which is another very light vehicle that sits up a little bit higher than that. There's a lot of data on this plot, but just bear with me and I'll explain a few key elements out of it. So blue one, we started with the Yaris. Okay, this is our blue dots here. So what we see as the water level increases, we go from quite a lot of traction in the dry case, and we get, as the water depth increases, we get to this point where it transitions and we get this steady decrease in available traction with water depth. So we did that with one person, but we actually had sandbags in the car to simulate, passengers in the vehicle. So the blue dots are with one passenger, the black dots are with 4 passengers. So unsurprisingly, we've got more weight in the vehicle, particularly over the back axle. So that takes more traction to move the vehicle. And here, the red dots, the red squares, we looked at, we had both axles tied. So we're dragging the whole car, the front and the back. And of course, we've got much more load on the front of the vehicle. So it takes a lot more traction to pull that vehicle to the side. Unsurprisingly, with our green triangles, this is our 4-wheel drive. We need much more, much bigger vehicle, takes much more water to fully float the rear of the vehicle. And, it's much more force to move the vehicle. Here's a little Festiva as well over here with the brown squares, or brown diamonds. Interestingly, and full credit to Stefan Felder for doing this, we're able to do this in a non-dimensional form. So we've got our, we're looking just at the water level above the pan of the vehicle. So when it first starts to begin to float, and on this axis we have the traction versus the weight of the vehicle. And amazingly, for 3 really quite different vehicles, they collapse down to quite a tight relationship. And so we can develop, fit a line through this for the data that we have, and we get this non-dimensional relationship between traction force and depth level. Another key thing that we looked at early in the study was the coefficient of friction between the tyres and the road surface. Now, floodwaters mobilise a lot of material. There's dirt, sand, gravel, debris, there's leaves, there's tree branches, there's a lot of stuff going down, and particularly with a causeway where it's coming from the channel up and over the causeway, really brings a lot of material over the road. So you can have a dramatic reduction in coefficient of friction. So we had a little look at that. We tested a number of cases, particularly looking at gravel and sand, how that behaved on concrete. Now, this was a really small part of the study, and I think we need a lot more effort around that. But for the work that we did, the very early study done by Bonham and Hattersley at WRL used came up with this conservative value of coefficient of friction of 0.3. And that's been used across a number of studies. And so this, the work that we did here basically confirmed that that was a suitably conservative value, but I also feel that we need a lot more work in understanding that. So we've developed this, body of information about, buoyancy and traction and coefficient of frictions. Now we wanted to have a look at what the hydrodynamic loading on the vehicle was. Now, there is a load of information about the coefficient of drag of a vehicle as it's driving through the air. It's clearly a thing that people are concerned about. They want to have vehicles be efficient. What happens when the flows are to the side of the vehicle? There's very little information, or I couldn't find anything. And also nothing on what would happen with water flows, where it's sort of only impacting part of the vehicle. So we were really interested in getting a measure of the coefficient of drag of the vehicle exposed to flows coming from the side. So we did it across a number of conditions. So subcritical flows, where you've got deep and slow flows. We did it for supercritical flows. That's where you've got very shallow and fast-moving flows. It tends to be what you'll get on slopes, you know, on a fairly steep sloping road like this. And you can see the water, you know, piling up against the side of the vehicle as it impacts that. And we saw that in the physical model as well. The last one is near critical flows. This is typically what you get in a broad crested weir, which would be, say, on a bridge or a causeway, where you get this kind of undular flow through here. So we did some testing, you know, in a similar kind of situation of that for the physical model. From that, we put all those results together and compared to try and get a suitable coefficient of drag that we could use for the rest of the study. So we can see that for supercritical flows, they're quite constant throughout a range of Froude numbers. Also near critical flows as well, we get a bit more scatter with the subcritical flows. That probably points to, you know, what's happening to the vehicle when it's very deep, that you might get a lot of variability. You know, supercritical flows tend to be very shallow. You're only talking about a small part of the vehicle. Subcritical flows, you know, might impact, you know, quite a lot of the up over the bonnet and things like that. So you might have quite a different coefficient of drag there. We also looked at how it relates to Reynolds number, and you can see that supercritical, near critical, and subcritical all tend to plot quite closely on this figure. So there's a nice, neat relationship between those, and also that it increases up to about 15,000, a Reynolds number of about 15,000, and drops away slightly. So from this, we took the average value of the drag coefficient and used that for later parts of the study. That's a real key outcome, because there's no very little information out there on drag coefficients of vehicles in floodwaters. So one of the real motivations for this project was to, you know, confirm the available our Australian guidelines for the safety of vehicle in floodwaters. So here we have our Australian rainfall and runoff guidelines for a small vehicle. That's this line down here, the dash line at the bottom, and for a large four-wheel drive here through here. And using the coefficient of drag that we developed from our model, coefficient of friction, so this is taking a very conservative, or taking a reasonably conservative value for coefficient of friction, and we plot out the results of our traction tests on that. So what we'll see here is that our Festiva with the brown squares and our Yaris, they both sit comfortably above the guideline value for a small vehicle. So the question is, do we need to move that line? Well, we certainly, you know, there's nothing from this study which shows that we would need to move that line down. Those two vehicles, you know, are both reasonably small vehicles, and they're sitting comfortably above that line. So there is space to work there with other vehicles. Could we push that line up? Well, then we're going to start thinking about study limitations. One is that we certainly didn't cover a broad spectrum of vehicles. We've only got 3 vehicles that we're looking at here. We're in lab conditions. We've got, you know, really perfect flow, and it's all quite well controlled. Although we've included some conservatism in our analysis, they're really, you know, there's a lot of situations there where, you know, things can be quite different. So, you know, particularly around like the rocking of a vehicle in floodwaters, and we also didn't consider uplift forces. So while we have really quite a good measure on the stability of these vehicles, there's, you know, we still need to have a bit of space here to give us a comfort zone. So our result from this was we recommended no change to AR&R guidelines without really, you know, you'd have to do a very extensive body of work to confidently change that line. Again, Stefan reduced those stability curves down to a non-dimensional value. So we're looking at Freud number on the x-axis, and again, the depth of the vehicle, the depth of water above the pan of the vehicle. And again, surprisingly, those results collapse down to quite a tight spread of data for the 3 vehicles that we tested. And so we end up with good general equation for the stability of vehicles in floodwaters. And I'm going to leave it there. I hope I've got across some really key points. You know, one is that the stability of the vehicles is really dramatically tied to that pan level of the vehicle. Once the water starts to touch the body of the vehicle, you very quickly start to have an unstable vehicle. That's probably one of the key take-home messages that I took from this.
Excellent. Thanks so much, Ben. Carlos can join us here in the background as well. In the meantime, keep those Q&A questions coming. I see a lot of great questions there. Quick over to you, Ben. Just a real quick answer on that one. As far as do you know whether car manufacturers are being required to consider flood safety as part of their design process at the moment?
I don't believe so.
Okay, so that's something that, you know, we hope to kind of advocate for that, because again, this is something that is, you know, one of the leading causes of the fatalities, at least here in Australia, and I think worldwide from the public service messages that I've seen. So Carlos is now going to address some design elements of this. We'll be talking about some of the Australian designs, but a lot of them are based on earlier designs and manuals and standards that are in the United States and adopted elsewhere around the world. So I hope this has relevance to you wherever you're coming to us from. So over to you, Carlos, if you want to go ahead and share your screen.
Okay, thank you so much once again for having me. And today I'm just really going to talk about, okay, we already talked about what happens to cars in floodways. I'm going to talk about the floodway itself. So my presentation will be currently a quick definition. What are the current guidelines in Queensland? How do we design floodways here? What is there to watch out? And then we will, I will touch 2 focuses that we take in design. One is resilience of the floodway itself, and another one serviceability. As I said, we do not advocate crossing floodways, so the roads are usually closed once they get water over it. Finally, I will conclude with just some other considerations that need to be taken when designing a floodway. So floodways are road sections that are designed to be overtopped by floodwaters without losing or compromising any structural integrity. So the immunity of these crossings could be really high, but usually even all the way to 5% AEP or 1 in 20 IRI for non-Australians. But effectively, at any point, any crossing can become a floodway, especially in large floodplains where you have experienced large and extreme events, as we are experiencing in Queensland. So I'm going to talk a little bit, not just floodways, but really low immunity level crossings. So current guidelines in Queensland, we have AUSTROS 2013, QDOM, of course, road drainage manual published in 2019, IRNR. There's some local council guidelines, and these Western Australian guidelines especially for scour remediation and rock protection as floodways. There's an impending update of the AUSTROS guide to this guide to road design, drainage, open channels, culverts, and floodways. But effectively, all these guidelines are still based on basic first principles published back in the day by the U.S. Federal Highway Administration and some local studies, Cameron McNamara, 1966, and even the new versions are based on that. So effectively, all the Australians probably familiar with this plot. So yes, a floodway can be designed using first principles. Weir equations, culvert equations, quite simplistic, as every single guideline in the state indicates. However, the reality is that we also do it, and mostly do it using either 1D or 2D models these days. Why? Because 2D models actually they present a better representation of overbank flows, multidirectional or skewed flows. However, we need to be very aware that 1D models are depth and width average, and 2D models are depth average. So because of that, there's always you need to take into account factors for variations in velocity. You need to be aware that definitely the velocity changes across the floodway. So first principles are still very relevant, and I recommend using them at least for checking your modeling results. So as I said, we in Queensland we focus both on in two aspects of the crossing: resilience and serviceability. So I'm going to be talking about this in the next slides. So first, resilience. Integrity, structural integrity of the floodway itself. But we don't want the floodway to be washed out by any flood. We have criteria, and I believe that is all the way to 2% AP, in some cases all the way to 1% AP, that we do not the integrity of any floodway to be destroyed. So guidelines currently say that minimum protection is grass batters. However, I hardly see any of those floodways anymore. Only in really low flying, really low flowing causeways, really small ones. So the 5 famous type of floodway design back from the US Highway Administration are still relevant. Probably the most common one and most popular also here in Queensland is type 1, which is effectively a concrete, reinforced concrete floodway, right? So all these designs are similar. However, they rely on the conditions of your flow. Is your flow free flowing? Is it wearing? Is it plunging downstream of the flow? Is it submerged? So you can vary depends on your conditions from type 1, type 2, type 3 if you don't want to go concrete, and then there's your type 4 and type 5. As I said, in terms of rock protection outside, upstream and downstream of the floodway, but there's different guidelines. Currently, guidelines point to the Western Australian guidelines, but we actually do recommend different sizing methods and obviously using engineering judgment, because all these equations, all these tables are provided in the guidelines are based on average velocity. So if you have a 2D model that more accurately depicts a maximum velocity, but you need to use your engineering judgment and see what is the velocity that you're going to use for designing your floodway. Right, so that's in terms of resilience. So we don't want the floodway to be washed out. In terms of serviceability, in Queensland, at least, it's a big issue when floodways or really low-lying roads are inundated for a long period, because actually they do impact in the cost of transport of goods, and also have a social impact on people moving in between places. So because of that, we actually focus a little bit on time of submergences, which is the period of time that the road is inundating during a flood event, no matter the depth. And we actually use it, it's expressed in hours, and we also use the ATOS, or average annual time of submergence. So we use these 2 parameters to actually try to come up what is the effect of flooding in not only respecting to stability of the embankment and the pavement, but also in the consequence and maintenance cost. They're also very important in to consider if the delays to traffic and not being able to communicate for societies is acceptable. So because of that, we in Queensland, the road drainage manual in Queensland has presents a methodology. It presents a methodology where, in roads that get inundated for weeks or months at a time, or in really low lying level crossings. So it is recommended to actually do a time of submergence analysis. So in these cases, it's very difficult to actually get a real calculation unless you have a gauge. If you have a gauge or you can perform a continuous simulation technique, then you are more, much closer to reality. However, there's ways to calculate TOS and ATOS that, although might not be exactly what the road experiences, at least allow you a comparison, provide you a parameter to see how bad in terms of time of submergence or immunity is your road. So as I said, Road Drainage Manual presents a methodology based, now it's in line with the 919, uses all ensembles and effectively recommends to use all the durations, to have a look in your hydrology for all the durations, and then come up with, for all your durations, then you need to go try to understand what is the largest mean time over your threshold flow. So you know your threshold flow or your overtopping flow at each crossing. So you do your durations. Normally when you do your hydrology model, you focus on peak flows, but you can now in here, that method recommends not to focus on peak flows, but on the mean time of submergences. It's important in here when using this is a theoretical method, yeah, and it's been around for a long time, since Osro's publications back in the day. But in here, when you are using the new 919, it's actually important to make sure that the time of submergence monotonically increases with event magnitude. So what I'm saying is that, well, it does not make sense that if you get a time of submergence smaller than for a larger event. So in those cases, you might actually need to be looking at not the critical duration, but at alternative durations that might give you the worst mean time over threshold. Right. So once again, once you calculate your time of submergence for different events, yeah, and including PMF. However, PMF is due to it has very little influence in this method, so it is okay to extrapolate it. So once you do that with probability density function, you can actually come up with your estimation of ATOS. And with those two parameters, what we do is we recommend to look, but not only at the one crossing. If you're only really looking at the one crossing, so be it. But in terms of connectivity, we actually recommend to look at a given stretch of road. So why? Because they do, obviously in places are close by, they actually not independent. So they are likely to be dependent. And when you start to try to make decisions about what to upgrade, well, it is a great tool to know which is the low-hanging fruit. So we call this kind of analysis, we call them flood link studies. And as I said, they are not only restrictive to floodways, but also to really low-lying roads, which of those we have a lot in Queensland. So what this kind of studies allow us to actually identify impacts and cost of flooding in low-lying roads and communities, yeah, and also cost and benefit of the proposed road upgrades. A question that I get asked all the time, well, which is the immunity criteria? Well, there's no standard. It cannot, depending on your location, you need to set an immunity criteria, yeah, because in some locations you need to basically achieve best value for money. There's always monetary constraints, but what you want is to always achieve best value for money with hydraulic performance and cost associated. Right. Very quick, I'm going to go through an example. After Cyclone Debbie in 2017, we have a lot of damage in the Gladstone region. So this is one of those floodways that were designed focusing on resilience because they were collapsed, they were damaged. So in this particular case, we had velocities of 3 to 4 meters per second based on 2D models, definitely. So road embankments and concrete slab destroyed. So I'm mentioning that because it's also important to actually think about the approaches, not just the floodway itself. Yep. So this is a photo of the same of the same floodway after restoration, where we actually to do this remediation, we really couldn't really improve the immunity a lot, but we improved slightly the immunity to actually focus on getting shorter time of submergences. We use a concrete floodway type 1, and we use heavy scour protection, heavy rock data scour protection. But the important thing is we also use a innovative approach called foam bitumen, which effectively is just a methodology that allows you to use a more flexible, more flood resilient pavement that can be used in the approaches. Yeah, this case is an on-seal road, so you see the floodway, and then you see the path of the seal road, and that is way beyond the floodway. Why? Because this damage actually happens in extreme events. So you need to think about how big is going to be your large event, so to guarantee the integrity of not only the floodway but the connectivity of the road as well, of the approach embankment, right? So quick video of how it looks now. So much better. We had also some big floods early on the year, and this held up well. So we're really happy with that. So I'm going to basically just leave it there, and I'm going to touch on other considerations that you need to do when designing a floodway. So you need to, at least in Queensland, you need to actually take into account the fish passage within the stream. You need to look at your river, your morphology, see what is happening with your banks, to make sure that the river is not moving on you, and you're not going to end up with a large scour in the creek itself. So when you do a design, have a look at your remediation measures, look at your extent, not only for small events, also try to see if you can large to extreme events, effect of climate change. So it's a big topic there, right? So do take it into account. We do take it into account over here. So definitely has an effect. So finally, safety of design and operation is important. In here, big safety media campaign. If it's flooded, forget it. So I'll just leave it there with showing one example where, well, this is not a floodway, but is very similar. So all this yeah, this is central west Queensland near Boulia, so with kilometers of road inundated for months. So all those designs actually relevant in this kind of infrastructure as well. So do take it into account. So with that, I'm going to leave it there, Craig. And yeah, happy to answer any questions.
Thanks. What you'll see in the background here, this is the video that Carlos was referring to. And again, just keep in mind, how would you try and provide flood immunity out here when it's submerged for this long? And, that mandate not to cross a flooded road would essentially, in this case, say, well, this road is unusable for that amount of time. So again, keep those things in mind. We'll have some clips running in the background here. Ben, if you can come back on as well. I've got about 10-15 minutes here now left for some Q&A questions. Have some great questions that have been coming in the background. So this is obviously a topic that is on people's minds, given the flooding, given climate change coming up. How resilient are we going to be? And let's try to prevent some of the loss of life that has happened previously through better design, better public awareness, and better information distribution, which is the whole point of this free webinar. Our Carlos and Penn have come on here, as volunteers. I'm a volunteer today. We are passing this free webinar along to you for the good of the industry. We would like to see these proper design practices implemented, and these public awareness campaigns distributed where they are needed most. So with that, over to you, Ben. I see you've answered a couple of questions in the background. Maybe just pick one or two of them to highlight, restate that for the listening audience that come in on the recording who won't be able to see it on the chat line.
Yeah, thanks, Craig. Yeah, there were a couple of interesting ones. First thing I'd really like to highlight from those questions is the first message is always don't drive in floodwater. It doesn't matter how you set up your vehicle, whether you're where you're trying to get guidelines in place for, safe design of vehicles in floodwaters, or whether it's an electric vehicle, or whether it's a front wheel drive or rear wheel drive, all of that doesn't matter. It does matter, but the key message is always don't drive in floodwaters. It's really just not safe. Even no matter how well you design the vehicle, there's still got that potential of being washed downstream, which is really the worst case scenario. There was one about rear wheel drive versus front wheel drive. Clearly, if you've got the engine at the front of the vehicle and you've got, very buoyant at the back, having a rear wheel drive is, you've got the potential of just completely losing all that drive traction. So that's an issue. Another one, there are a couple of questions around the velocity of the vehicle, and that is, maybe I didn't really express that very well. The flow velocity is really important, and the loading on the vehicle increases with the velocity squared. So if you double the flow velocity, if you go from 2 meters a second to 4 meters a second, you've got 4 times the loading on the vehicle. So the velocity is really important, and that's a massive problem for us in the field. I work in the laboratory and I see flows every day, right? I couldn't walk down to a stream and tell you whether the flows were 2 meters a second or 3 meters a second. It's really hard to judge. And so, again, it comes down to don't drive through floodwaters. But for professionals that need to, for emergency services, they do at times need to do it. They've got, large, well-equipped vehicles that are highly trained, and they need to, save people's lives, and they've got the equipment to do it. And it's really important that we give them the right kind of tools to be able to measure that velocity so they can make an assessment about whether it's safe for them to go into floodwaters.
No, excellent. Thanks for that. I might highlight a webinar that we did a few months back, where I'll put a poll question up and just remind everybody what happened here. When we asked, a couple of hundred practicing professionals in the water sector, and this had to do with rock sizing, but think about what it takes to move a particle. And as Ben mentioned, squaring, doubling the velocity, squares basically the diameter of the material that you could move. But how does that affect the weight? We asked this question to the audience, and it turned out that everybody got this answer wrong. There was not a single attendee who got this question right, and that is a factor of 64. It is the cubic quadratic, and it is raised to the 6th power. So the size of a vehicle that you could potentially move with increased velocity can certainly, it's very sensitive to that. Carlos, in the background, anything that you wanted to cover that you've answered on the chat line for us?
Yeah, thanks, great. Yeah, that's one, a couple of questions regarding design floodway design. One is what standards will be used for culvert fish passage in this kind of structures. Well, here in Queensland, the Department of Agriculture and Fisheries has guidelines relating to fish passage in culverts. They state that velocities larger than 0.3 meters per second actually restrict passage of the smaller species of fish. So DTMR has standard treatments to implement in this kind of culverts where fish passage is an issue. Most of them so far consist on baffles, in implementing actually baffles into culverts. There's other ones. There's UNSW as well is doing some good work looking at that with other devices, but so far over here, the standard treatment is actually using baffles to actually create extra roughness, create more opportunity for fishes to avoid the larger velocities within culverts. And the other one is how to decide if a vented causeway is better than a pay for in a particular site. Well, that's a good question, difficult to answer. It depends on a lot of factors. It really depends on monetary constraints, serviceability, road users, how many users are using that road, and how the importance of that of actually using that. If you actually if that crossing is deemed very important for connectivity within the community, then obviously a concrete a pay for concreted floodway is a better solution. Yeah, but I get it completely. In other places, it's just not affordable, and you can probably live without it.
No, thanks. No, appreciate that, and appreciate all the questions that have been coming in. We might run just a couple minutes over. I hope this isn't too distracting in the background. We've just got a bunch of clips showing. And if you can take what you've learned from Ben and Carlos and predict with some of these cases, the motorcycle, the trucks, the buses, the emergency vehicles, try and predict which one is going to make it and which one isn't. Don't test that yourself, as Ben mentioned. You know, we don't want anybody pushing it here, and there are various public safety campaigns that we'll put around out there. You know, there is the Flooded Forget It one that we've chosen to highlight today. There's the 15 to Float one that I've seen as well. There's Turn Around, Don't Drown in the U.S. Any other ones that you're aware of, please pop that into the chat line. We'll add that to the resources for this website. So, and it's not just you know, it's not just vehicles. You know, some people have, I've heard the rule of thumb, if you wouldn't walk through it, if it's going to knock you off your feet, it could probably float your vehicle as well. And there are actually some people who have volunteered themselves to test this or start the pumping here. Achtbaan in Dutch is a roller coaster. You know, this is, you know, when we talk about these flood safety things and depth times velocity, we talk about pedestrians as well as buildings, even though today we focused mainly on the vehicles. Let's see, Carlos, do you have any that you've highlighted here that you wanted to hit? I'd see more than we can probably get to in the next couple of minutes.
Another question that I got to ask is there any guidelines for different category of roads on how much should be the flow of water over the carriageway or the ford to allow any vehicles to cross the road? The question is, my answer is very simple. In question, there's no water allowed. So
Yes.
not at all. In Queensland, if there's water on the road should be closed, at least in theory. So don't we're moving away from that. So if it's flooded, forget it. So we TMI, or at least no Queensland authority will ever recommend any safe passage. As long as there's a little bit of water, the road is closed.
Yes, and thanks. That's the message to get across. And it comes back to our poll question again. You know, what it takes to float a car is not necessarily advocating that's the safe depth to cross. And so that's kind of a message to get across. Ben, anything you wanted to cover here as well?
Yeah, there's some comments in there about improving signage and cameras on floodways as well, so people can plan their trips. I think they're great ideas, and there's lots of work being done in that area, not by myself and others here, but other parts. Lots of work around Australia's great work around Australia is being done on getting that messaging right, and you know, making it easier for people to make those good decisions.
No, excellent. And you know, one of these things, these clips that I'm showing here, we focused on this one a little bit in one of our tech webinars a while back. And again, if you can get public safety in mind, I'll just scroll through some of these things here, where you get people inside of these vehicles at a conference and have them try to see what happens when the floodwaters hit them. And we'll include links to these in the show notes below on the YouTube video, along with some recent papers at the FMA conference covering, where should we be drawing our depths and velocities from, 1D models versus 2D models versus 3D models. Yeah, the guidance probably needs to be updated in some cases. So all of these resources that you see here, I'm posting here to this website called hydroschool.com/floodway. And we've got links that we'll be posting to every one of the resources that we've touched on today, including the video clips, so where you can see it in a little more detail. So with that, I'll have closing remarks then. We're just about out of time. Let's go back to Carlos and then Ben for just your closing. I know you already had your take-home messages in your presentation, but let's do a take-home message to pull this whole thing together and send people on their way. If we can go over to you first, Carlos, and then over to Ben, and then in the background, Joel, if you want to start showing the the screens on some of the links that you'll have available to you for additional training and webinars. So Carlos, bring it home for us.
Yeah, so as I said, once again, if it's flooded, forget it. But if you're interested in the road, so look not only at the causeway, but also at the approaches, because that's where usually things start to fail. So yeah, in your design, include the approaches. Make sure that your approaches are resilient, not just the structure per se, bridge, causeway, culvert, etc.
Excellent. Ben, closing remarks.
It's real simple. Just stay out of floodwater. Stay safe.
Yeah, and I hope you've seen enough examples here where if you went back to that question that we answered at the beginning, that we don't equate that depth of buoyancy with the safe depth to cross. That's probably the take-home message. Look at some of these examples. People have lost their lives over us. This is serious business, and we have the opportunity as practitioners in the water sector to make a difference so that next time around when there's a flood, maybe we won't have the kinds of statistics that we've seen even this year here in Australia. So with that, we thank all of you for your participation. The recording will be made available to you. Those who attended, you can also get your professional development hours by attending these webinars now and in the future. So look at what's coming. Do fill out the survey. Help us shape what's going on, what we're going to cover in future webinars and courses. And then you'll see a whole list of courses here and webinars coming up. You know, these are what's on the books, on the agenda for now. What's coming after these is up to you. So fill out the polls for us, fill out these feedback forms. Do let us know. We appreciate your attendance and your participation. This is a great group to be affiliated with, and I appreciate the opportunity to participate with Carlos and Ben. Thanks so much for your time. We'll see you next time around on the Australian
Thank you, everyone.
School. Thank you.
Thanks, everyone. Thanks, Craig.
Thank you. Thank you, Craig. Cheers. Bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.